So I wanted to mention one thing which I think I had sort of said last time, but I'm not sure I said it entirely explicitly, which is somewhere near the end of the last lecture, we defined the components. I mean, as you know, we took great care to define the notion of vector in a geometrical way. And then at the end, we defined the components of the vector with respect to a coordinate chart. What I didn't do explicitly is show how the components would change from when you pass from one coordinate chart to another. But that's easily, almost trivially worked out from the way that we define the components. But what I wanted to mention is, of course, that in a lot of cases, especially in older books, you actually see vectors defined in terms of components and how they transform from one chart to another, or they might say one coordinate system to another. Of course, that would be yet another possible definition of a vector, but it's not the one that we used because it's the one that's the sort of least anschaulich. It's the one that is least geometrical would be a better way of saying it. It obscures the simple geometrical meaning of the vector. But I should have mentioned that as yet a third possible definition of vector. So the first one is the one we used, which was a vector as infinitesimal displacement, rigorously speaking, an equivalence class of curves through a point, as we saw. Another one that's sometimes used is this derivation definition, which I mentioned. And of course, the third and maybe the oldest one in the context of differential geometry is the one where it's a set of components, just a set of four numbers that associated with a coordinate system that transform in a certain given way when you change the coordinate system, which so the way I proceeded was to some extent an attempt to avoid that definition, or to give a more, as I say, a more intrinsic definition than what that would lead you to. Then when we come to tensors, we'll see that tensors are naturally thought of as products of vectors or sums of products of vectors, and have also a geometrical meaning in that sense, which can also be brought out even more in terms of pictures. Thanks. And there's also a news homework somewhere circulating around that you can. Okay, so speaking of tensors, we were now, the thing we just finished with was we were defining the line element last time. I had defined ds or ds squared sometimes. It's easier to work with, which was equal to g alpha beta dx alpha dx beta. So here we had defined it in order to shortcut some of the necessary mathematical preparation. We had defined the metric the information that's contained in the metric tensor, which is what gives the geometrical content to space-time. We had defined it just in terms of components in a coordinate chart. So exactly, if you like, doing what I said I was avoiding doing in the case of a vector. And I've done that in order to get to some of the physics more quickly, and then we'll come back and do it more intrinsically, in which we will see that this really is a tensor. For now, it's just a bunch of, it's just a matrix, a 4x4 matrix, associated to each coordinate chart. Okay. In the same way, so the line element, of course, is crucial. Metric tensor, it allows you to do many things, but most importantly, what this allows you to do is talk about proper time along a world line. You know that even in special relativity, the proper time along a world line is given by the integral of this ds, where this GAB is the flat metric, the Minkowski metric. And that's true whether or not it's a straight line or a curved line for an arbitrary time-like world line. And the same thing will be true in curved space, based on the equivalence principle, that locally you don't see whether you're in curved or flat space, and the clock does whatever it would have done without knowing about the curvature. You could design well, can come back to this, but you could design clocks that would be sensitive to the curvature, but you wouldn't call them good clocks from the point of view of relativity. The other thing that we need, along with the line element, and again I'll use this sort of quick and dirty way or opportunistic way of defining it, is the volume element, dV, which allows us to associate to a portion of space, an infinitesimal portion of space-time, a volume, and that, of course, is crucial for doing integrals, and integrals are crucial, in particular, for writing down the action functionals, the gravitational action and the matter action as well. So we need an expression for the volume element as well, although we won't be using it for the moment. We'll be using much more the line element when we come to derive or present the Einstein equations. Then we'll be using this heavily. Or when if we were writing down, which we won't for a while, equations for field as opposed to particles, again we would be using this heavily to define the action. But since it fits naturally here, let me define it now. So again, we have a coordinate chart. So it's a coordinate chart, which I'll call eta, mapping M into R4. Since it's a coordinate chart, we put here R4 as a codomain. If you want to picture what we're doing here, is we have, as usual, our chart. And we have within it, we just have a little, I don't know how to, we just have a little portion of this, so small that it's essentially infinitesimal, and we want to know the volume of that little portion. So that's what the volume element does for us. And we'll assume, the reason I call this eta is because eta somehow corresponds to y in the usual choices of letters that people make. And I'll call the coordinates of this, as we did before, y mu. So we'll represent an element of R4, which is 4 real numbers, just by the coordinates y nu. And this will be, there'll be some point here, P, within the manifold M, at which we're interested in computing infinitesimal volumes around that point P. And as before, again invoking in effect the equivalence principle, we'll assume that in the coordinates y mu, so we choose a special kind of coordinate chart in which we've assumed exists when we were defining the line element. That's, if you like, a physical input to the theory in which the line element is given by this. And in the same way, we know the element of volume, right? Because if we're in flat space-time, then we know the element of volume. If these are the usual, these kind of Cartesian coordinates, then we know that the element volume is, when we have to integrate things in Minkowski space, we just integrate d4y, which if you would write it out in the integral, under the integral sign, it would be dy0, dy1, dy2, and dy3. But usually it's just written as d4y. And this is true. This fact that this equality is true only at P, just as when we define the line element, this equality is true only at the point P. As soon as you get away from the point P, it becomes more complicated. So now, how does I wanted to make one other tiny comment. Here I've written the chart as going from the manifold to R4. When I was being more careful, this is what the Bourbaki group popularized under the name of abusive notation, if you want to be strictly correct. Another way of saying it is it's a slightly sloppy notation, because in the mathematical conventions that are most commonly used, this would mean that that eta has as its domain the whole of the manifold. But we know, in fact, it has only the domain, in general, some subset of the manifold, some open set, which before I called U sub eta. So if you wanted to be really pedantic, you should say that it maps U sub eta into R4. But by saying it like this, I think the meaning is clear. So after a while, all these precise distinctions that we make when you're in introducing the subject, usually they become kind of a burden and use shortcuts. So here's an example. So now I'm just going to write that eta is a map of M into R4, even though its domain is smaller. Okay, so now, how would this line element look in an arbitrary chart around the point P? So we saw, if it's a volume element, the line element, we saw it looks like this, where this is some more general 4x4 matrix. Not any 4x4 matrix. It has to be, of course, symmetric. And more importantly, it has to have the right signature. That is, it has to be of the form, I won't write it again, but it has to be the form, the Jacobian matrix acting on eta mu nu, where eta mu nu is the -1, 1, 1, 1. Maybe I'll write that again. Okay. So now, in the same sense, if this is how in the flat coordinate chart, how does the volume element? If this is how it looks there, how does it look in the general coordinate chart, which I'll call Xi, with coordinate x? So let Xi, another chart, which is also a coordinate chart, but whose coordinates I'll call x, coordinates in R4 here. In the case of Xi, I'll call them x. Well, that's easy because we know dv is equal to, dv, I just wrote it, it's d4y. You should think of this always as being under an integral sign. We're trying to integrate something or other. Then, if you change variables from y to x in the integral sign, in an integral, you know what the result is. It's equal to just d4x times dy dx, where this dy dx is short for the Jacobian matrix. So it's the determinant of partial y, say, mu partial x alpha. And then you have to, by the usual conventions, you think of this as always positive, and so you need to take the absolute value of the determinant, right? So that's a very familiar, yeah.
So the determinant comes from the fact that it's actually a volume form and not just dx is multiplying each other, and then you get the antisymmetry of the different derivatives multiplying each other.
You're asking where this comes from? You're telling us where this comes from.
I think I am.
Yes, okay, that's fine. I think there's different ways of thinking about it. I'll say something in a second of geometrically how we haven't yet derived the formula, but we're about to do so for dv. Then when we write it down, I'll give my take on what's the geometrical meaning, which I don't think the passage to forms necessarily actually clarifies the situation. It's not wrong or anything, but I don't think it quite clarifies the thing. I mean, we knew how to, when you do multivariate calculus, you know how to do integrals, and you don't actually have to introduce forms. And it turns out that introducing forms, this is kind of side comment, but it turns out that introducing forms is really awkward when you have to integrate over non-orientable manifolds. You would have to replace them by something called axial forms. What's actually simpler is scalar density, at least in my opinion, although it's not most people do use forms, I agree, but I think actually scalar, what people often did in the past was use scalar densities instead of forms. They're kind of dual objects. But there's this orientation issue buried in there. But that's certainly one way of thinking about it. That's true. But there's another way of thinking about them is directly in terms of measures of volume, and which are scalar densities. We won't actually define scalar density now, and I'm not sure we'll ever have time to do it correctly mathematically, but that's, I think, underlying what's going on. So just imagine some ink or something that you've poured onto the manifold. In some places there's more ink, in some places there's less ink. That's a scalar density, right? And it actually has a direct meaning without introducing forms. But now the question, well, okay, so let's just stick with this for the moment. And now this gives us what is dV, but it gives us dV only. It gives us only dV at the point P. And in order to actually interpret this at the point P, we have to go and introduce some coordinate chart y or eta in terms of which the metric takes this simple form, the sort of local. It's like the locally freely falling frame at the point P. If you had to do that, go at each possible P, introduce a different y, it would be obviously a mess. It's much nicer if we can write an expression that doesn't refer to y directly or to a directly, but just works in terms of what's available in the coordinate chart xi, the x chart, which is this metric tensor g alpha beta. So can we do everything in the coordinate chart xi with coordinate x? And the answer is, this is really where you're relating to your comment. The answer is we can by what looks now will look here like a trick, although it does actually have a geometric meaning. So let's go back to the expression. So we'll leave this hanging for a moment. We want to rewrite dV in a way involving just the variables available in the chart xi. Now let's go back to something that we already know, which was the expression for g alpha beta. Remember, we derived it in relation to the same chart eta. We derived it by what will look like a very familiar formula. Right? If you look back at from the last lecture, or it's probably a formula you know in any case. But this we derive. Now, if we think of these as matrices, we're dealing with three matrices: eta, mu, nu, a symmetric matrix, this Jacobian matrix, matrix of the partial derivatives, and this Jacobian matrix. If you're careful with the order of the indices, you would have to say that this has the form of some matrix times eta times the transpose of that matrix, right? Because you have to if you made the convention that alpha came first, for example, then it's alpha mu, eta mu nu, but then it would be beta nu. That's the wrong order, so you had to make a transpose. So anyway, this has the general form of a sort of J eta J transpose for some matrix J. Now suppose we take the determinant. Of course, we see here that what we're after is the determinant of partial y, partial x. So let's take, this is an equation we have, let's take its determinant, because you know the rule for the products of determinants. So this implies that the determinant of g alpha beta, the matrix, is equal to the determinant of eta as a matrix times this determinant of the partial y, partial x comes twice, squared, right? Because there's two factors of this. And of course, the determinant of a transpose is also equal to the determinant of the original matrix. And this is equal to -1, of course. Here's the -1 is the Lorentzian nature of the metric. And it's the same whether or not you use 1 minus and 3 pluses or 1 plus and 3 minuses. Okay. for the signature of the metric. So now if we take the square root of this, so this is allowing us to get out of the determinant. If we take the square root, we have to put minus the determinant of G alpha beta. Since the determinant of G alpha beta is always a negative number, as you see here, but minus it, that's a positive number. So we're just taking the square root of its absolute value. That's equal to the absolute value of the determinant of partial y, partial x. And that's what we needed here, right? So just plugging this result, this allows us to replace this determinant here by the square root of the determinant of the metric tensor. And the conclusion in the end is that the volume element is then given by the determinant of minus, by the square root of minus the determinant of G alpha beta times d4x. So that's the main result we need. This is the volume. This is how you can integrate at least scalars over a manifold, a Lorentzian manifold. But yes.
The metric eta is only valid at the point P.
That's right. So that's a good point, right? So this equation that I wrote down is only valid at the point P. I mean, I've only derived it at the point P. But then how do you know where P is? See, now I've re-expressed everything in terms of things available at the chart, in the chart C. So I can go to any point, and there will be some chart eta which is valid, for which that equation is, all these equations are valid, and that'll tell us that dV is still given by the same expression. So that's what. So by this trick, we've freed that expression for dV from dependence, from explicit dependence on the chart eta, and then this is then valid at any coordinate chart.
So this equation is valid as long as on the entire chart.
Yes, it's valid exactly on the entire chart. Now you might have seen it in a slightly different form. Sometimes people just write G for the determinant of G alpha beta, and then with that notation, of course, you would just see root minus G times d4x is given the volume element. And that's the way you'll most commonly see it, but of course what it really means, it's just a shorthand notation for this determinant. Another thing is sometimes I might, if you want to remind yourself explicitly of what dimension manifold you're in, you might put a little 4 there to show that it's 4 volume. Okay, so that's the other form of the result. So, any more questions on that? So now, although we freed this expression from dependence on the particular chart y and eta at P, it still depends on the chart C. I mean, it still only makes sense in a chart. Actually, what these G alpha beta are, as we'll see in a little bit, are a tensor, or more precisely, they're the components of a certain tensor, which we call the metric tensor. And so I just mentioned G alpha beta. We won't be able to make this precise until we've defined tensor. It's called the metric tensor. And in the same way, this is what I was just referring to before, is what's called a scalar density, which is a fancy word meaning something that you can integrate. That we won't be able to make precise until much later if we ever do, but you'll run across this terminology, and it's actually what's called a scalar density of weight 1 plus 1. What it really means is it has the character of a volume, and so if something of weight 2 would have the character of a volume squared, and so on, and something of weight minus 1 would have the character of an inverse volume, which is actually, I wasn't going to say this, but I'll say this. V4x, if you ask what that is, it's actually a scalar density of weight minus 1. It has the character of an inverse volume. That's why when you multiply them together, you get something that's a true scalar. Yeah. So when I said that scalar density has the character of a volume, I should have said, if that's what I said, I should have said a volume density. I mean, it's a density of volume. So when you integrate it, you get an actual volume. So once you know all these facts, then you see directly that ds, the line element, the infinitesimal distance, and dv, the infinitesimal volume, are scalars. Now, where does this come from geometrically? So this is the side comment. So this would be my response to you, or my take on the same issue that you were raising. Where do these formulas come from? So the formula for ds squared is, this is just a parenthesis, it's really just a Pythagorean theorem, right? It comes from Pythagoras, the Pythagorean theorem. It comes from the idea that distances have this character, that they didn't have to, but physics has taught us that they do, not only in space, but also in space-time. And in other words, a fancy name for that is that the metric tensor, whose components are G, is what's called a pseudo-Riemannian tensor, pseudo-Riemannian metric. Riemannian because of this Pythagorean nature, and pseudo because it has one minus sign. It's Lorentzian. The formula for dv comes from something, this is very familiar, everyone learns this early on. We know that distances, infinitesimal distances, with respect to a basis are just, an orthonormal basis are just given by the sum of the squares. That's this. The other one comes from another fact that's maybe well known, but not as well known, which is that it's a formula for the volume of, I don't know what you call this, a cuboid, or I think there's a fancy word, parallelopiped or something like that. Anyway, but I mean just something that you take three vectors and you take the shape that they span. I can't even draw it very well, but what do I have to do? Something like that. If it had, so suppose that it's spanned by vectors v1, v2, v3, and in our case v4. What is the volume of this object in terms of the vectors that span it, just in flat space? Okay, so I don't know how many people have seen this formula, but there's a formula for the squared volume. In Euclidean space, this would just be a plus sign. Well, it would still depend, no, what am I saying? It would still depend on the order of the, so let's keep it as plus or minus volume squared is given by, no, I'm getting confused about the sign. Is the sign always, no, yeah, I guess it has to be, has to keep this plus or minus. So the volume squared is given by, it's the matrix of all the inner products. This should have said v1 dot v1, v1 dot v. In the case of 4, we'll have v1 dot v4, and so on. This means the determinant. And down here we'll have v4 dot v1, and here v4 dot v4, right? So is that a familiar formula? People look sort of blank. What?
It's like a generalization of v1 cross v2.
It's a generalization of the square of that, right? So that'll give you that'll in 3 dimensions, which is special. That'll give you the volume more directly, but this gives you the square of the volume. So maybe it's not so well known. But anyway, So I was thinking to actually derive this. Maybe we will at some point, or maybe we won't have time. But it's not too hard to derive this by induction, using the fact that the volume of some solid is equal to the area of its base times its height. And then you can introduce an orthonormal basis by an induction. You can prove, anyway, this formula is true if you know this, and this formula is just a purely geometric formula that's valid in flat space. If you know this, then you can derive, I would claim that this is where, you see there's a determinant here. That's where that's the ultimate origin of this determinant that shows up here, here, in the definition of the volume form. If you think of a little bit of the manifold marked out by basis vectors, we have in a coordinate chart, we haven't defined them yet, but basis vectors in a coordinate chart, and you want to know what its volume is, then you need to take these infinitesimal basis vectors, make this determinant. And if you see what that is, because the inner products of the basis vectors in terms give what are actually directly gives the components of the metric tensor, you'll see that this root determinant of the metric tensor is this geometrical object. And I would claim that's where it comes from. At least that's one way. That's in a different way than what you suggested of thinking of where it comes from. They're really sort of dual to each other, the two approaches. Okay, but the main thing is we have these two expressions for the line element and the volume element. Now what can we do we'll be using the line element now, because in a little bit we want to discuss particle motion and reference frames and clocks and so on, and how they respond to curvature and acceleration of the reference frame. So to do that, we'll need we'll need a formula for the proper time read by a clock, and more generally, length along a curve. It's basically in order to define length along a curve that we introduce the line element. So how do we do that? We introduce a parameterized, the basic formula I should really write first. So this is the increment of proper time along a little bit of the curve, and that's equal to the absolute value of ds, which is the same thing as the square root of the absolute value of ds squared. And that's, of course, equal to, for a time-like curve, minus ds squared to the 1/2. Okay. So that I'm just reminding you, this is because ds squared for time-like is negative. So this is the time-like case. Or light-like, but in the light-like case, of course, it'll just give 0 by definition. So now if we want to write, so that's the basic fact, which we derived in effect last time. But if we want to be more careful about how to define a curve, say, we can go back to this picture, we have the real line, we have our manifold M, we have a map gamma, which is usually have called gamma, I think, giving you the curve in the manifold. And then in that, within that manifold, there's this chart C. So this is U sub C. And over here, there's now it's a coordinate chart, so it's R4. There's the image of that neighborhood of the point P here that the curve is passing through. And this, I guess, we called U tilde sub C. And within that, there's the image of the curve. Okay. All familiar stuff. This is the manifold M. And this map is C. So when you put it all together, we have a map of the real line, or if you want to not abuse the notation, so-called, you could have an interval here. It may be only some compact interval over which, so in other words, it's a finite curve with endpoints. Then we have a map of this interval of the real line, or of this interval I, into the real numbers. So we have 4 numbers, x mu, which is equal to gamma, which is equal to, what notation am I using? I think I'm using the notation I introduced before. You have the 4 coordinate functions mapping, which is xi. So xi is more, the map xi looks like 4 coordinate, or it defines, and can be defined in terms of 4 coordinate functions, x mu. And so this is x mu of gamma of lambda, called little x mu. Okay. And then we want to say, of course, that the curve is smooth, and you remember how we defined that. That meant that this map from R to B, which is R4, should be smooth. And so all that really means in this coordinate language is that all the derivatives, dx mu, d lambda, x mu being given by this, and d squared x mu, d lambda squared, make this a little x, and so on, should all exist. So if we plug all that in, and if we plug in the formula for the line element ds, all it tells us is that the length of the curve is equal to the integral with respect to d lambda, which is the parameter for the curve, of minus g mu nu, evaluated at gamma of lambda. Usually don't bother to write that argument explicitly. Dx mu d lambda dx nu d lambda to the minus 1/2, right? So that's the formula for length, and I've assumed here really that it's time-like in writing this minus sign. Otherwise, I just should really be putting here an absolute value. But the physical meaning of the space-like length is a much less direct thing along a curve than it is in the time-like case. So one thing that yeah? Yes, I certainly want, sorry, I don't know why I wrote minus 1/2. Here's the minus, yeah. Should be plus 1/2, thanks. And if I had not, it's a good thing you said that, because the next thing I was about to say would be even more wrong, which is, would be another error, which is that you notice here that the d lambdas actually cancel out. We just introduced it for the sake of not having to write infinitesimals. But if you're happy with writing infinitesimals, then you just leave out the d lambdas and you just write this, which is directly our expression for the line element, right? So I just got this by introducing the d lambda in appropriate places. So this is nice, but it's still tied to a chart. Now, in order to express all this in a more intrinsic manner, we need the notion of tensor. That is, we want to say what this g mu nu means geometrically, and in order to do that, we need the notion of the metric tensor. So that's the next thing. We also need the notion of vectors to talk about these, but we've already talked about vectors. So we need the notion of vector, but we need to supplement it by the notion of tensor. What we'll see in this first illustration of the fact is that these g mu nus can be viewed as the components of a tensor. We won't see that fully until we've discussed tensors more extensively, but we'll see here the first application. We can basically think of these as corresponding to what's called the metric tensor. Okay. So what is that? So let's go back and think of what the line element does. So we take our usual manifold M, and the tangent space to M, tangent bundle. Think of a particular point in M and a tangent vector to M at that point, which I'll just call V. It's obvious that the line element assigns a length. Knowing the formula for the line element, we can find the length of an infinitesimal displacement to which V is the corresponding finite vector, and that'll give us a notion of length to V. So it'll give us what we could call the length of V. And conversely, you can probably easily convince yourself that if we know this length for every vector V, then we know what the line element is. Well, it's trivial. It's obvious we know what the line element is. However, a metric is not just any old rule for defining a length to a vector. It has this special character, which is this quadratic character that comes from the Pythagorean theorem, or this generalization here of the Pythagorean theorem. So a metric is a rule for assigning lengths to vectors, but it has to be defined quadratically, in a quadratic nature. And basically, it's a rule that says ds squared. So given, let me first draw. So here's a curve gamma, for example. Here's a tangent vector to that curve gamma, and think of a sort of epsilon times it. So this dp, if this was a parameterized curve, then it's v times d lambda. Okay. So that, as usual, v is just the derivative version of the infinitesimal displacement dp. So given that, ds squared is something that depends on this infinitesimal displacement dp, but it does so in a quadratic way. That's what this notation is meant to indicate. So I'm, where, when I write this now, what is G actually? I'll write this in a fancy way. G is a map from takes pairs of tangent vectors into the real line, which is bilinear. So what do I mean by bilinear? I mean, do I have to define bilinear, or everyone is happy with it?
Is it linear in both?
Yes, it means linear in both arguments. So bilinear means it means that G of, say, V1 plus V2 comma V3 is equal to GV1 comma V3 plus G of V2 comma V3. So that's the statement that it's linear in the first argument. So I put a sum here, but I hold the second argument fixed. And then, of course, this G is also symmetric. So G of V1 comma V2 is equal to G of V2 comma V1. So therefore, given that it's symmetric, it's also linear in its second argument. And that's what bilinear means. If we write this, if we now divide through everything by d lambda squared, we get ds squared over d lambda squared is equal to G of dp. I can bring the d lambdas in because of the bilinearity. I can bring these d lambdas inside, right? So that's the other thing that I didn't write, but it also means that it means that G of lambda times V1 of lambda times V1 comma V2 is equal to lambda times G of V1 comma v2, right? I mean, this one is more or less really just a trivial consequence of that one, if you think of continuity. But anyway, that's what bilinearity strictly means. So I can bring this, when I divide through by d lambda, I can bring it inside, and then that's just g of v of v. So this is what I meant by saying that the line element assigns a length to every vector. If we take the square root of both sides, then the vector v is being assigned the length, the square root of g of v times v. So if we imagine just any old rule that does this, so such a g, now forget where I got g from. Just think of a rule that assigns to every pair of infinitesimal displacements a number in such a way that it's bilinear. So such a rule g with two arguments like that is called a metric tensor. We'll see later that any bilinear map from vectors to scalars is a tensor, and more generally, any multilinear map from vectors to scalars is also a tensor. In fact, some people define tensors that way. Now, so here we said. So now let's suppose we have such a bilinear map. Is it clear? I'm not sure. Let me say a little more. Hopefully it's more or less clear that this bilinear map is equivalent to the line element and vice versa. But let me just say that more completely explicitly. So we'll take it, as before, we'll take a chart that maps C into R4, a coordinate chart. And then we have what I want to do is, in effect, show that these 16 numbers, G alpha beta, I want to show that, in effect, they're the components of this bilinear form, this metric tensor G. So remember that if we remember this map C star that we defined, which takes vectors. Where's our manifold? It takes, remember we had the map C, which takes the manifold into, takes a point of the manifold into a point of the vector space, V, which is R4 in this case. We also had a map, which I called C star, which is basically, in a sense, the derivative of the map C, which takes vectors in the manifold, tangent vectors, into vectors in the vector space R4. Remember the definition of that, and that's the map in terms of which we defined components. And what it told us was that C star of GP is equal to D of X mu, where X mu are the four, as always, the four coordinates associated with the chart C. Okay, that was what we found before, what we had before. If we just plug that in, then we get, given this bilinear form dp, bilinear form G acting on dp, which is equal to ds squared. If that bilinear form came from if it does correspond to the line element, then we have this equation. We divide through, as before, by d lambda. You like to work with vectors. So remember so now these things, these derivatives, we call the components of V, which was gamma dot of lambda. These we call the components of V in the chart Xi. What am I? By the same token, that's basically from this equation. If we divide this equation through, if we divide this equation through by lambda, then it says Xi of V, Xi star of V is equal to dx mu d lambda. So therefore, these things are the components of V, i.e. they're given by Xi star of V. By the same token, we can call these 16 numbers G alpha beta, we can call the components of the bilinear form G. And if we turn it around, this is giving us, this came when I plugged in the same dp, d lambda, in both slots of G. But I could plug in any two vectors here, and that would allow us to form an inner product between any two vectors. I just plug in the components of any two vectors I like. So this is then called components of the metric tensor. So by G here, I mean the metric tensor. I don't mean its determinants, but to avoid confusing notation, I'll put the slots here identically. So remember, the metric tensor was this bilinear rule for giving pairs of vectors real number. And so its components just come in a way that we'll see by plugging in basis vectors. But the result will be that you get these G alpha betas. For now, this is just a definition. The G alpha betas are the components of G. Whereas this statement that the dx beta d lambda are the components of V, that's actually not a definition, it's a theorem that follows from the way we define components of a vector. When we define components of a tensor, more generally, this will also become a theorem. So the main thing to take away from this is that the notion of line element and the notion of metric tensor are essentially identical. They're interchangeable. From one you can get the other and vice versa. Okay. Now metric in line with what I've been doing before, I want to stress still that the metric tensor is a geometrical object just as much as a vector is a geometrical object. And as I said, when we come to talk about tensors more generally, we see that it can be written as a sum of product of vectors. But another thing that makes a geometrical object geometrical is that if you can make a picture of it somehow. So just as we make a picture of a vector by taking a little line and put an arrow on it, we can make a picture of a tensor, and that'll illustrate, or make a picture of the line element, and that'll illustrate in what sense the metric tensor is a geometrical thing. So how would we do that? So this is pictures of metric tensors. So let's do it. The simplest case is where we're dealing with a Euclidean space, not a Lorentzian space, not like Minkowski space, but just like ordinary space. And just for purposes of the picture, let me take it to be two-dimensional instead of one-dimensional, and think of a manifold, say a surface in 3 space, which is a manifold with the Riemannian metric, with a positive definite metric, and then think of the tangent vector, and think of this vector space. I could do this in general in any vector space, but the case of interest for us will be where that vector space is the tangent space to a manifold. So how would I draw a picture of a tensor? There's probably of a metric tensor. So that would be, if we were in 2 dimensions, we'd have G alpha beta like this. It would be some 2 by 2 matrix with positive and diagonal and positive determinants. How would I make a picture of that? Well, I claim that it can be represented as a kind of ellipse. Why is that? Well, consider the ellipse of unit vectors. So it's just the set, it's just a circle basically, what you would call a circle. It consists of all, you take the origin of this plane, which is some point P in the manifold, and then it corresponds to some point P in the manifold. And then you take all the tangent vectors of length 1 and draw what their locus. Okay, so that's a circle, but in a general coordinate system, which is what we have here, this G alpha beta is not necessarily diagonal, and so it looks like an ellipse. It's just, if you think about it, it's the equation of an ellipse. You could think of these as the infinitesimal circle. If you think of the vectors as infinitesimal displacements, it's just an infinitesimal circle about the point. So that's a picture of a, that's one interpretation. It just considers, it consists of all, this consists of all the point y, such that G alpha beta y alpha y beta equals 1. If you know what this circle is, then you know what is G alpha beta and vice versa. So this is a purely geometrical structure that carries the information of a tensor. What about the case, that's just one way of, this is a mathematical definition. There's other symmetric tensors that arise in physics, not just the metric tensor. For example, some of you may be, if you've studied continuous median elasticity, you may be used to the stress tensor, T. So suppose it was the stress tensor, T alpha beta. In the same way, you could represent that by an ellipse, and you may have seen that in some books. There's something called this, I think, the stress ellipsoid or something like that. That would be in 3 dimensions. That's, again, it's just a picture of the stress tensor, T alpha beta. What about the Lorentzian case? We can use exactly the same trick, except to make it look interesting, we really have to go up to 3 dimensions. So again, we have this vector space. Now I'll have it with the signature plus. Of course, I could have done this in 3 dimensions, just that I can't really draw ellipsoids as well as I can draw ellipses. But here we have to try, because let's do the same. Let's draw the picture, the locus of all vectors whose norm is -1. So in this case, we'll take the locus of all vectors such that GVV is equal to -1. Or G, if you like, put G alpha beta, Y beta is -1. And what does it look like? Well, we know this is just special relativity, right? We know there's the light cone. This is the unit, these are the sort of the 4-dimensional velocity vectors, or the unit time-like vectors. And of course, it's just, everything is squared here, so we also have the negative pointing, backward pointing time-like vectors. That double hyperboloid is a picture of the metric tensor eta alpha beta, say, or G, or more generally, G alpha beta. If it's G alpha beta, this won't look round, it'll look ellipsoidal, just like here, but it'll be the same picture, an ellipsoidal cone and a hyperboloid tangent to it. I mean, what's the word? Asymptotes to it. So that's a picture of a Lorentzian metric, one possible picture. In general, There are many possible pictures for a geometrical object, but this is simple, fairly simple one. Notice also that implicit in this is the light cone, because that's just the the cone to which this hyperboloid asymptotes. And of course, so the light cone has quite a lot of information about the metric. We'll see the importance of this in a second. It has quite a lot of information, but what it doesn't tell you is which. I mean, here's another hyperboloid, say where I normalize it to 2. That's also asymptoting to the same light cone. So if you just know the light cone, you don't quite know which hyperboloid you have. That means you don't quite know you don't quite know the normalization. You don't know the normalization, but you do know it up to an overall scale. So actually, if you just know the light cones, you get a tremendous amount of information about the metric tensor. That's almost a picture already of the metric tensor, but we need a little addition here. So I wanted to mention that we won't probably encounter this at all in the course, but there's a notion of spinor that everyone has at least heard of if they're not familiar with. And there's a lot of confusion about what is the geometrical meaning or lack of geometrical meaning of a spinor, and how do you correctly define covariant derivative in a spinor. And it also somehow becomes clear if you think of the spinor geometrically, and there are nice geometrical pictures for spinors analogous to these, known in one particular case for a Weil spinor. It's called a null flag. Anyway, so it's useful to keep in mind that whenever you encounter a geometrical object, which most things in space-time physics are, in the continuum anyway, then it's useful to try and actually make it explicitly geometrical by such a picture. One last notation thing. I've been writing the metric like this to show that it's a function of 2 arguments, bilinear form as it's called, or a bilinear operation that takes 2 vectors and gives you a number. But that's kind of awkward to write all the time. It's not so easy to see these dots and so on. So what I'll usually do when I refer to it is just write it like this, which, if you don't look closely, it just looks like the components of the metric tensor in a coordinate chart. But if you look very closely, you'll see that I used Roman letters here, and I've been using Greek letters before. And that's related to something called the abstract index notation, which we'll forget about for now, but is very useful to keep in mind. It makes a very useful notation, which probably, in effect, at some point I'll start using. And then after a while, I won't, like everyone, after a while I won't bother to distinguish between the abstract indices and the concrete. But anyway, so for now, when I refer to the metric, I'll often write it like that, to mean the metric itself, meaning this bilinear form, and not meaning its components. So are there any questions about the metric? Any more questions? Okay, so let's again see where we were. We were sort of cataloging, going through a catalog of the different mathematical structures that make space-time what it is in general relativity. And in virtue of the equivalence principle, they're all some sort of curvy generalizations of the structures that Minkowski space has, flat space. Because general relativity is a local theory, and because locally it's equivalent at some order to flat space, really its structures are all direct generalizations of the structures that define Minkowski space. And so we started with its topology, then its smooth structure. In other words, we had notion of convergence, and we had a notion of vector derivative, if you like. And then now we've just given the geometrical structures in the more narrow sense, the lengths and so on, lengths, distances, and angles, all of which you can define once you have this metric. the only one we really defined were the line element and the volume directly. And then there's the fourth structure, which is the causal structure. That Minkowski space has. So what is it? It's in the case of Minkowski space, and even in the case of continuum general relativity, it's closely tied to the metric, so that sometimes people don't bother to think of it as a separate structure. But actually, when you're actually working with just in the theory of relativity itself, it's very useful to make this distinction, so that the proofs of most of the singularity theorems, the theorems that tell you that if matter starts collapse and if the collapse is violent enough, as it would be say inside a Schwarzschild black hole, once you get inside the horizon, when the collapse becomes violent enough, nothing can reverse it, for example. That's an example of what's called a singularity theorem in relativity. If you look into the proofs of the singularity theorems, you'll see that they're largely reasoning about this causal structure. That's the essence of them. There's also another fundamental theorem of general relativity is called the positive energy theorem, that tells you that any collection of gravitational waves or of matter, as long as the matter itself has positive local energy, and if the space-time is asymptotically flat so that you can define the total energy, then the total energy will always be positive. This kind of guarantee of the stability of general relativity. That has different kinds of proofs. Some use spinors heavily, which I refer, but there's one proof which actually is very analogous to the singularity theorem proofs, and it again uses the causal structure. So the causal structure is a key to understanding many of the most basic aspects of relativity. It's also, some of us think, the most basic structure that space-time has, more basic than all the others. And this is an old tradition that goes back to the very beginnings of relativity theory, if not earlier. And if it is the most basic structure, then it's the one that has the greatest chance of still retaining a meaning in quantum gravity, where you're going beyond, if you're going beyond the continuum manifold of general relativity, which is what most people expect to happen. So all those are reasons for thinking about the causal structure as a structure in itself. And what is it mathematically? It's what's called a relation, which is often written like this. It looks like a less than sign, but it's supposed to be a little bit curly. In tech, it's that thing, precedes, precedence.
Thank you.
Oh, you just, I see, now you're checking everything. That's impressive. Okay, so it's a relation on the manifold M, which tells you which points of M, which points of the manifold of space-time can possibly send signals to which other points, or which can influence which other points, if you like. Or you can say, so there's different languages you can use for it. Well, this signaling is a basic concept of relativity theory. It's a basic postulate, I guess you could call it, that you can't signal faster than light. So, and that's what this relation codifies. There's another word for it that's often used in the language of partial orders, which is ancestor. So if you say that x precedes y, it means that you could signal from x to y. You could send it, something that happens at x could be felt at y, could be detected at y. You can also use the language that x is, in a certain sense, an ancestor of y. All of these things point to the one axiom, one of the two big axioms that such a precedence relation has to satisfy, which is transitivity. That means that if x precedes y and y precedes z, then x precedes z. I should have called them, actually, since if I use the kind of notation I was using, I should say P precedes Q, since I've been using this kind of letters for points of the manifold, then it implies that P precedes R. Okay. Now the there's another thing which I'll come to a second called acyclicity, but this is one of the basic structures that a causal order should have, basic properties that a causal order should have. The equivalence principle tells us, so for the moment, just for a second, forget the metric. We just say space-time it's so constructed that certain events can influence certain other events and certain ones cannot influence certain other events. That we express by this. But as we know, that's closely related to the light cones. It's another postulate that the causal structure is given by the light cones. And so the equivalence principle tells us locally what the causal order is. So it tells us that locally, and this is a very familiar picture, I'm sure, to everyone, given an event P, there are those events Q which it can signal to, and they're the ones in the interior or maybe on the future light cone. And there's the events R to which it cannot signal. And so in this case, we'd have P precedes Q, P does not precede R. And the way the convention is, the way this symbol is defined, also if R is in the past, we say that it does not precede, we say P does not precede R. So basically those points that represent the future of P are those in or on the light cone. And there's a notation for that. Sorry. The equivalence principle tells us that, I mean, in Minkowski space, that's what we have. The equivalence principle then tells us that the same should be true locally in the curved space-time. So what that means is that in the, in a curved manner, so now think of it, the full space-time, which is in general curved, it means that locally there will always be a little light cone living in the tangent space to that point. But these light cones don't have to be all parallel or whatever. They can point in all different directions, but they move around in that sense. But locally there's always a light cone. And so if we want to know if some point P precedes some point Q, which in this case I'll say that it does, what we really ask is whether there's some curve gamma that goes from P to Q in such a way that locally all along the curve gamma, it's staying within its future light cone. So another way of saying that is that gamma is what's called a causal curve. And causal means either time-like or light-like. We call it time-like if its tangent vector is everywhere time-like, that is, that its length, the tangent vector, the g of eta. So if so time-like means that g. So we take the tangent vectors of the curve. So I'll just call that gamma dot, as we've been doing sometimes. So that means g of gamma dot is less than 0. And light-like, of course, means that g of gamma dot is equal to 0. So the tangent vector is a null vector in the light-like. It's on the light cone. And in the other case, it's on the it's within the light cone. In either of those cases, we call it a causal curve. And if there's a causal curve from P to Q, then it means that P precedes, in this case, it means that P precedes Q. If there's no causal curve, then it means that P does not precede Q. So once we have the metric, we can derive this causal structure. With one addition, we need to know which is the future direction and which is the past direction. So in some sense, the metric GAB plus some choice of sign, telling which is the future half and which is the past half of the light cone, is equivalent to a causal structure. Or let's say it's not equivalent to yet, but let's say it determines the causal structure of space-time. Also, in case you, to what extent you can go back, we'll say in a second. Also, in case you read some of these things that I referred to, let me just mention the notation. There's actually two small variations on the same theme of this causal order that people have defined. Well, actually, more than two, but there's two main ones. One is called I plus, and one is called J plus. And the one I've defined for you here when I said causal curve is actually what they call J plus. If you demand that the curve be everywhere time-like, then it's called I plus. So it's a little bit stronger. So I plus basically includes the interior of the light cone, but not the light cone itself. Whereas, and there's another one, K plus. It's kind of interesting. But I won't go into any detail because we won't be needing it just now. But what I will say something more about is the notion of causality conditions. And this shows in what way the causal structure. It shows one way in which a causal structure is not, in all cases, the same thing as a metric, or almost the same thing as a metric. So what is this causality condition? If you just think of a Lorentzian manifold, it's just some manifold that has this Lorentzian metric in it. It has a line element. So it has light cones everywhere. But what it doesn't tell you, what that doesn't exclude is time loops or causal loops. So you can imagine imagine Minkowski space in 2 dimensions. Okay? And now so this is a portion of Minkowski space. And now make a periodic identification in time. So it's like taking a strip like this and identifying the future in half. That's also a Lorentzian manifold. It has a metric. So on the light cones look like this everywhere, constant. And yet from a causal point of view, it's pathological because you can now go from a point in space-time. If you say that this can send a signal to its future, but its future now becomes its past, then it can signal to itself. Not only can it signal to itself, but once you're back here, you can go off in that direction, still inside the light cone, and so you can signal to points space-like to you as well. You can signal faster than light, basically. So you can signal both faster than light and into the past, if this were the causal structure. And so it wouldn't be compatible with the idea of causality, really. And so people call it usually, I don't know, I forget the word, pathological or acausal or something like that. So normally we put extra conditions on the space-time which says that shouldn't happen. You shouldn't be able to signal into your past. And that, but there are many small variations on which conditions you put. But the simplest thing is to say is that this causal relation is acyclic, which is just what I said. There are no cycles. So that you cannot have, it does not happen that you have like P precedes Q, and Q precedes R, and R precedes P. Okay, that shouldn't happen. And by transitivity, if P precedes Q and Q precedes R and R precedes, then this transitivity actually implies that Q precedes P. So you don't need a string of many, many points. It's enough to say that it never happens that P precedes Q and Q precedes P. So that's called acyclicity. And when you have that, then the causal structure, when you have acyclicity and transitivity. So let's see. So transitive plus acyclic, that equals what's called a partial order, or a poset for short. So the statement, what this causality conditions are telling you is that space-time forms a poset, a partially ordered set. So it should be both transitive. And then one last comment, one last fact about the relationship between. So in this picture, we saw that the causal structure, because it tells you where the light cones are, actually gives you a lot of information about the metric. The exact statement is that, so let's review what this means. It means if we have the topology plus the differentiable structure plus the metric, all these things we need in order to define the metric, plus the sign, this sign is the future versus past sign. It's a choice of what's future and what's past. By the way, there are even more pathological spacetimes. See, at this spacetime, we still have a direction. We still have a future direction, although it doesn't mean much because you can go from the future into the past. But you can still distinguish locally which is the future direction and which is the past direction. If you want to amuse yourself in this way, you can try and cook up a spacetime in which you can't even consistently distinguish future from past. Then this sign wouldn't even make sense. Think, for example, of a Mobius strip. That'll give you a clue how you might think of such a spacetime. Those are called time. Those, if you can distinguish locally future from past in a consistent way, that's called a time-orientable spacetime. If you give it an orientation, you say which is future and which is past. That's that sign. Those other pathological ones are called non-orientable. You can't even make a consistent choice. Anyway, if you have all these things, then it determines, as we've seen, a causal structure for this space-time, although it might be pathological unless we assume the acyclicity condition also. Conversely, so from now on I will assume always the acyclicity condition without saying it explicitly. Conversely, this also determines a volume element. Of course, that's direct from the metric. That's what we just did before. The reason I've added it is that if I add it, then I can also go back. So if I have the volume element and I have the causal structure, then I get all these other things for free. This is a kind of remarkable thing because it's just such a simple thing, just a relation between pairs of points of the space-time. No fancy stuff like tangent vectors and differentiable maps. And in concept, it's a very, very simple thing. But if you actually have it for the space-time, you can recover from it all these things. So if you're interested in that, you might ask yourself, how would I recover the topology? The answer to that goes by the name of Alexandrov topology. It's one of the early discussions in causal structure of space-time. It's also closely related, as it turns out, to computer science by some amazing coincidence. But anyway, so that seems probably a good place to stop. Is there any questions on what we've just said about causal structure? Okay, so let me give you the reading for next time. I thought we would make a start on it today, but we didn't quite get to it. But this is what we'll start on next time. And it's what you might call the theory of clocks, particles, and exploring the metric with the aid of matter. And you might also think of it as how does the metric affect matter and its motion? The converse thing, how does the matter affect the metric, is the Einstein equation, which will only come later. So the reading for next time would be walled pages. I hope these pages are good. 43 to 45, 77, and section 2.3 to 2.4. And Schutz sections 7.2 to 7.3, 2.4, 2.6 to 2.8. This should be in the nature of review for everyone, hopefully. And then all of chapter 3. I could take 5 minutes and start talking about it, but it doesn't seem worth it. So did everyone hand in, who might have come late, hand in their homework and or get one of the homework? It's also posted on the website in the homework if you didn't get one here. If you're watching this and not actually here, you can get it from the website.